Okay, let's continue with our look at forming operations, and we're going to move from metals now to plastics. So there are 5 basic forming operations for plastics that we're going to look at in this chapter. Thermoforming being the most common, extrusion being up there as well, blow molding, calendaring, and mechanical forming. So first up is thermoforming. So thermoforming, we're going to be using a thermoplastic sheet, right? Remember, thermoplastic is the plastic that can be heated up and allowed to cool and then reheated. So we have that ability to shape it rather than a thermoset, which is going to degrade with the application of heat. And so it's not going to work as well in a thermoforming operation. Thermoforming is extremely common. You can see it in the everyday kitchen and food containers that we use all the time. In the figure here, you can see the cups and the plates and all this stuff. It's a very simple process. It doesn't require high forces. It doesn't require high heat. It has a very short lead time. It doesn't require special types of machines or dyes or anything like that. So it's generally very inexpensive. It produces, it has a high rate of production if you needed to make things very fast. And you can also have some variability in its textures and finishes as well as colors. So it's a very, very common and useful production process for plastics. Now we're going to revisit. We've already seen a chart like this or a graph like this when we were looking at the casting operations for plastics. So now we're going to kind of use the same concepts and ideas, but we're going to be looking more at the forming operations for this. So just to understand this chart again, you know, we at the beginning here, on the left-hand side of the chart, these are low temperatures, right? So this is where the plastic is in its normal state, right? We haven't raised the temperature enough to make it flexible or pliable, okay? So as we raise the temperature, then it's going to become more flexible, and as it becomes more flexible, then what that means is that we could see the chart, the axis on the y-axis here, the vertical axis, is really showing us how much force is required to bend or to reshape the material. And you can see that as the temperature goes up, it becomes more pliable, right? There's less force required to reshape it. And then we get this rubbery plateau where it kind of evens out, and then it turns into like a liquid, right? Or an extremely pliable, flexible material. So this temperature right here, where it starts to dip down, we call this the glass transition temperature, okay? So this is where it goes from our normal plastic to a flexible plastic, and it becomes more and more flexible as we move higher and higher past the glass transition temperature, until we get to where we start to plateau off and we get the rubbery flow. This is called the softening temperature, okay? So basically for thermoforming, what we want to do is we want to operate within this range, in between the glass transition temperature. That is to say, we want to raise the temperature just enough so that the material becomes flexible, but we don't want to get it so high, the temperature so high, that it can't hold its shape, okay? And so that's our thermoforming temperature range. Now, our preferred thermoplastic properties, right? Remember that there's a wide range of plastics and a wide range of properties for those plastics. So what we want in a thermoforming operation is we want a sharp glass transition temperature. That is to say, we want it to drop off like as near to vertical as we can, right? You can see here we have a little bit of a slope. Ideally, we want it to drop off straight, and you can see that in this kind of example right there where we're dropping off straight. So we want that. because that's going to give us a sharp differentiation between the normal state of the plastic and where it becomes able to be thermoformed easily. We also want a large difference between the glass transition temperature and the softening temperature, right? The larger this temperature range separation is, the easier it's going to be to operate, right? If the glass transition temperature is very close to the softening temperature, then we run the risk of going past the softening temperature with an imprecise control of temperature, and kind of messing up our flow, messing up our plastic. So we want a big difference between the TG and the TS. And then we also want a constant stiffness or viscosity between TG and TS. Now, what does that mean? That means that, let's go back here. This rubbery plateau is really good. So if we have a drop off and then straight into a rubbery plateau, that would be ideal. Okay. Now, understand that the ideal plastic or thermoplastic is probably not something that exists, but these are parameters that we work from. So typical plastics that are very well suited to thermoforming include plastics with a high molecular weight and amorphous plastics. So that includes polystyrene, ABS, polyvinyl chloride, PMMA, and polycarbonate. Those difficult to thermoform include the semi-crystalline plastics. So high density polyethylene, polypropylene, and PET. Those are difficult but not impossible to thermoform. So there's a couple of rules for thermoforming when you're trying to set up a thermoforming operation. And the first one is the conservation of volume. Okay, so just like all forming operations, we're not talking about removing material or adding material. Okay, so that is to say the amount of material we start with is going to be more or less the amount of material that we finish with. All right, and so that means we have volume conserved. So if we start with a certain volume of plastic, we're going to end up with a certain volume of plastic. And that has to be taken into account given the change in geometry, because that's really what we're talking about. We're going to start with one volume of plastic in a geometry, and then we're going to change that geometry, but the volume isn't changing. So we have to understand that very well. A couple of other assumptions that help us along that way. We have a clear boundary between the cold material of the mold and the warm material of the thermoform sheet. And we'll see this in figures and in the videos that you watched. And then we also make an assumption that wall thickness is constant everywhere. Now, in reality, wall thickness is not constant everywhere. Okay. And that's something that you do have to be concerned with. And you can kind of see it in this example of this cutaway of a thermoform sheet. So basically what you're going to expect, what you're going to see is that the corners are where we get a thinning of material versus the straight sides where we don't get a thinning. So one thing that we have to be aware of is that the corners, the radii here, are all going to exhibit a thinning of material. All right. And so when we talk about the law of conservation of volume, we're dealing with average wall thicknesses because we can't really go in, except after the fact, and predict exactly what the thicknesses are going to be, and then therefore the volumes. Okay. So constant wall thickness is almost impossible to realize except for very sharp radii. So the thermoforming process, you can kind of imagine what it would be. It's not a very complex process. The first thing we do is we need to heat the material, and we're doing that here. So the material here is in sheet form, and there's a conveyor belt traveling from left to right, right? And the sheet material is going to go through a oven, and that oven is going to heat it precisely, right? So it's going to heat it above the glass transition temperature, but not past the softening temperature. And then it's going to be carried on to the molding area. And so here we have an upper and lower die mold, right? And these two are going to come together and it's going to form the shape. Now notice as soon as we leave the oven, the heating area, it's going to start to cool. So this has to be relatively controlled, relatively quick. You know, we can't dawdle here or else it's going to cool too much. So it's going to be reshaped through the mold and then it's going to be taken over to the next step. The part is formed here and then we're going to release the part in the mold. So this is the demolding. So cooling happens and then we demold it, right? We don't want to demold it. We don't want to take it out of the mold too quickly or else it won't hold its shape. So we want it to cool sufficiently so that it comes back out of the glass transition temperature, right? It goes below that again. And then we're going to clean it up, trim it, whatever we need to do. All right. So 5 basic shapes, something that you could probably imagine if you wanted to, you know, do a thermoforming operation yourself. By the way, I should say that I remember when I was growing up, we did a thermoforming operation in our house as kind of a afternoon of fun. We used to have a whole bunch of records, right? So I don't know whether any of you have records anymore, but you know, we had a whole bunch of records as I was growing up. And what we would do is we would take the record, you know, the large record, like 12 inches in diameter, something like that, and we would put it in the oven over a metal like mixing bowl, okay? And then you'd put it in the oven at, I don't know what temperature, you know, I was young, so I wasn't in control of anything. So let's just say 200 degrees, right? We put it in the oven for 200 degrees, and what would happen is the vinyl record would melt and form over the bowl, and then we just take it out of the oven and let it cool, and voila, we had a bowl made out of a record. And that was an early example of a thermoforming process. I'm not saying that you should do that on your at home, you know, but yeah, if you have any records, you know, you might look into it. It makes a pretty cool bowl. You do have to you do have to watch because there's a hole in the middle of the record, so it's not going to hold any liquid, right? Because it would come right out. All right, so looking at the different thermoforming processes, we have a positive forming process, and this is where the sheet is draped over a positive mold, right? We call this a positive mold because like a cylinder is a positive cylinder, like a pin is a positive cylinder. The mold is something that we can touch, right? So we can touch this mold shape, right? And that makes the shape. The other option here is a negative forming operation. And this is called a negative forming operation because we're using the negative mold, right? We're using a hole in the shape of what we want to create. And the idea here, this is a negative because you can't touch the negative of the mold, the hole, so to speak. I know I'm you know, getting a little bit out of bounds here, but you should understand what I'm talking about here. Notice in both of these situations, we're going to use airflow. With the positive forming, we're going to use a vacuum, right? You can see the vacuum here. The vacuum is going to help to pull the pliable plastic sheet over the positive mold, right? So it's going to pull it down. With the negative mold or negative forming process, we're going to use a positive air supply on the top to blow down, and then we're going to use a negative or a vacuum on the bottom to help it pull it into shape. Okay, so those are the two different types of thermoforming processes: a positive forming and a negative forming process. This is, I think, a little bit more of what we talked about, just the process. You have the preheated plastic sheet. It's placed down on the shape and then it's clamped, right? And then we have air pressure that blows in while a vacuum pump pulls air out, and it's going to form it to the sides. This is very suitable to complex shapes because of the bidirectional air, because you're using a positive airflow above and a negative airflow below. You're really able to suck and blow that shape into the mold crevices so that you get really good shape adhesion and dimensional stability that way. This is more of the same. Okay, just another way to look at it. So moving on to the cooling stage, right? This is where the hot sheet is pressed against the cold mold, so it's going to instantly start to cool when it's pressed against the cold mold, and cool below the glass transition temperature. Cooling time is going to depend on the local part thickness. Now, what that means is the thickness of the part at the specific areas where it's in contact. So a thicker cross-section is going to cool slower than a thinner cross-section. And you need to be aware of that when in a thermoforming operation, because you don't want to remove it too fast, right? Because then you'll have areas of the part that have solidified, but areas that are still flexible, right? And then that's just going to mess up the shape. You also have to consider the type of plastic and also the mold material. Wooden molds can take longer to cool, right? They're more insulative. Aluminum molds with intercooling means we have water running through to cool the dies, are going to be for very quick cooling and high volume production. Obviously, these types of molds with the intercooling cost much more than the wooden molds where you're doing prototyping in short runs. I've also seen 3D printed molds, right? So you can 3D print molds now, which is a very good way to do prototyping in short runs. One of the things with 3D printed molds is the 3D printed surface often has layering. So you need to, if the surface of the plastic the part that you want to make, if you need to control the surface quality or surface finish, then you need to address that with the mold. So if you're using a 3D printed mold, you might have to finish that a little nicer. You might have to sand it. You might have to do some other operation to make that mold smooth. If you don't really care about that, for prototyping or whatever, then you don't need to worry about that. One thing it is you need to note, though, is that whatever surface there exists on the side of the mold cavity, right, you're going to pick that surface up on your plastic part. So pre-stretch forming is kind of a variation on the negative and positive forming, and this is where the heated sheet is blown away from the mold, pre-stretching it before the forming stage. Now, the reason why you would do this is because you really want to get, kind of like a bounce. If you have an intricate shape, and you can see that in this example here, we have a lot of contours, a lot of different curves. So if you don't do a pre-stretching operation, what happens is the thermoform sheet is going to touch on the mold cavity and instantly start to cool. And that may inhibit how it's able to drape across the rest of the geometry. So this pre-stretch actually increases its stretch, right? So that it actually becomes longer, right? You can see that this shape, this arc, is a longer material than if it was just straight across here. So now we have additional material that we've kind of gotten out of the situation or put into the process through this pre-stretch. And then, so we blow the air up, we get a pre-stretch, and then we're going to apply pressure and blow the air down, and also use vacuum to pull it to the sides to get that. So this is done with highly complex molds. Obviously, it increases cycle time, right? So when we're talking about high volume production, understand that seconds or even half seconds can add when you're running 10,000 or 100,000 parts times a half a second. that takes minutes away, and maybe even more than that. Plugassist forming is kind of a combination of a positive and negative forming operation. So we have a negative forming operation, right? We have the sheet stretched over a negative die, right? A negative mold. And then we're going to use this plug to kind of push it down, okay? And this is going to help us have a lower cycle time, right? Because we're kind of forcing it in. It adds in, or it aids in deep form. So if the mold is very deep, we might have trouble getting the sheet to pull down into it very quickly or very accurately. So the plug can really help with that. It also controls thickness. Now understand, going back to our concept of the mold cooling it as soon as it touches it. Understand that we can also have a mold that is heated to some extent. So it doesn't right away cool the shape down, and it aids in getting it stretched out. So in the Plugassist thermoforming, the heated sheet is blown. This is kind of a combination of the Plugassist and the Prestretch, right? So we have Plugassist and Prestretch. In this case, the heated sheet is blown away from the mold, right? So we're pre-stretching it. It's going to come in contact with the cold plug and thereby stick or, kind of become in contact and kind of stay there because of the difference in temperature. And then it's going to force it down with the plug. Now, what you get here, remember that as soon as the temperature of the plastic changes to less than the glass transition temperature, it stops to stretch. So if we don't want this area right here to stretch any further, right, then on the pre-stretch, when it hits the cold plug, it's going to stop stretching. And all the remaining stretch is going to be carried out in the periphery of the part. So, this is really a process, thermoforming, where you're going to run through a lot of trials, right? Understand that you have a lot of tools that you can choose, a lot of different production processes, but this is something where you're going to have to go through trials. You're going to be making parts, cutting them in half to look at them, trying to ascertain where thicknesses are thin and thick on the walls, and how you can adjust that. So it's a simple process, but there's a lot of complexity once you get into the nitty-gritty. A two-sheet thermoforming process, I guess you can kind of see we have two sheets. Interestingly is how these two sheets are kind of, I should say, welded together, right? It's kind of a weld, right? The heated plastic on the sides is going to be joined together and pressed so that they more or less form a welded joint here. So we can make airtight plastic containers, right? These are used in boats. These are used in coolers. You might even be able to fill this with an insulating material after the fact. So this is thermoforming using two heated sheets and a different upper and lower die that are going to make these shapes come together. All right, now moving on to extrusion blow molding. So extrusion blow molding is the type of molding. This is really a thermoforming, right? But it's thermoforming to create specific geometry. In this case, think water bottles, right? Those plastic water bottles that everybody has, that you see them all over the place now. These are done using this process. So the first step in this process is we heat the plastic and we extrude it into a hollow tube, right? So the plastic is going to come in here, it's going to be heated, and we're extruding it down into this hollow tube. This hollow tube is called a parison. Then we're going to clamp the sides together, right? So the sides come together, and we're going to pinch off the bottom. So now we have a hollow plastic tube that's heated, okay? Then we're going to inject air. This is the air tube. We're going to inject air into this hollow plastic tube where the bottom is sealed. The air is going to pump out the plastic and it's going to form into the bottle-shaped die. All right, so there, fourth step, we fill and it fills the die. And then we're going to open the die and we're going to release the now formed plastic bottle and trim off any excess from the bottom and the top. Now, what's interesting is if you have some water bottles around, go and have a look at them. Look at the bottom of the water bottle. See if you can find that little, it almost looks like a navel, right? Like a belly button. Go and look at the bottom and see if you can find the area where the blow mold, where the mold was pinched and then cut off the extra shape. See if you can find that. And there is your finished product. There's some variation here. This is another process where the injection mold is heated in this. Then we're going to secure the mold, the plastic in the mold, inject the air in it, blow it up again into the mold shape, and then we have the finished bottle. What's the difference between this and the previous one? Well, notice that this has no extra shape on the bottom. So in this case, and also we're not trimming the top, so there's no trimming. So in this case, what we're starting with is we're starting with a preformed blank that is the exact amount of material that we need to create the bottle. All right. As opposed, now hold on just a second, let me go back. As opposed to this, which we have a extruded shape that's kind of a continuous extrusion, right? Continuous extrusion. So we're just going to pinch it off when we have enough, when we have a sufficient amount, and then we're going to trim it later. So with this type of operation, there's no trimming involved. All right. So same process, just what we start with. And that's it. So in the next operation, we'll look at the last topic, which is forming powdered metal. All right. See you then.